So at this point, I'd like to introduce our feature. Now that our housekeeping details are over, I would like to introduce our guest speaker. Carrick Eggleston is the department head for WPI's Civil and Environmental Engineering Department. He joined WPI in 2019. Just prior to WPI, Professor Eggleston was the department head for the Department of Geology and Geophysics at the University of Wyoming, and had taught across the globe in such countries as India, France, and Switzerland. He has a myriad of fellowships, editorial, and patent credits to his name, and upwards of 84 conference presentations and 75 publications under his belt. Professor Eggleston has an AB in Earth Sciences from Dartmouth College and earned his PhD in Applied Earth Sciences from Stanford University. We're thrilled to have him here tonight, and I turn the program over to Carrick.
Hello, and thank you, Peter, for that kind introduction. I am very glad to be at WPI. We were both attracted by WPI's project-based curriculum and theory and practice philosophy. It's been a wonderful place for us to be. So I'm very happy this evening to talk to you a little bit about our carbon emissions, global climate change, and our ongoing global energy transition. I got to this through studying minerals in geology and geophysics, particularly iron oxides, which are one of the cheapest possible materials that are semiconducting and absorb visible light for solar energy applications. And so it's a little bit of an unusual pathway, but that got me into talking about or wondering about our global energy and carbon trajectory. So I'm starting in a somewhat unusual location in this subject. First of all, I don't want to start with the doom and gloom because there's plenty of that out there. I want to start with the good news and what is going on. But this picture on this slide is of coastal Scotland, just east of Edinburgh. And on this date, September 21st, in 1745, the Battle of Prestonpans took place on the field delineated by these blue lines, and I've got a picture from the Outlander television series that depicted that battle in 2016. But this area is famous for other things as well. This was the start of the modern history of coal mining. In about 1200, some monks digging some black rocks out of the hillside discovered that they would burn, and there has been coal mining for 800 plus years since then, up until quite recently. Also, you see in this picture, John Kane over on the lower left, who in 2017, when we visited, is giving us a tour of the National Mining Museum of Scotland. When he was 15 years old, he started working in a local coal mine, going more than 1,000 feet underground with a hand pick to dig coal out of the small coal seams. So this area has a very long history of coal mining that ended recently. And on the battlefield, you can see there's a little roadway running across the middle with some trees along it. That is the bed of a trackway that was built in 1722 to bring coal from the town of Trinent over on my right and behind me down toward the coast. It's called the Battle of Prestonpans because of the pans, big iron pans. They used wind machines to pump seawater and used the coal to evaporate seawater for salt, which was important in food preservation at the time. You also see the power lines, two sets of them running across the battlefield toward what remains of a coal-fired power plant. And when this was all built in 1963, the local population was more interested in the jobs and less interested in the battle. But since the power plant shut down and the massive wind development in Scotland, the last coal-fired power plant shut down in Scotland in 2016, and yet Scotland still exports 25% of the electricity it generates because of massive wind power development. There is a large offshore wind power project that wants to bring the power onshore at this location and use these no longer used power lines. But to do that, they'd have to build a power substation on part of the former battlefield. And the local population now, particularly because of the Prestonpans television episode, want to memorialize the battle and build a visitor center like other battlefield sites in Scotland, and build on the tourism potential of the phenomenon we now know as Outlander tourism in Scotland. So this is a primary location, just one example of the many ways in which renewable energy development builds on former fossil fuel history with connections to social science and stakeholders that may be a bit surprising and are different from location to location. So next slide, please. Also in Scotland, in the upper left, you see the in the red line, the rapid decline of oil production from the North Sea, the UK part. Aberdeen, Scotland is the center of the oil and gas industry in the UK, and production is dropping off. So when we brought students there in 2018, the students were flabbergasted to learn from the newly elected Conservative City Council members who were former oil executives, that they consider oil on the way out and that the economy of the area needs to remake itself. And one of the ways they're doing that is to use the large amounts of wind power, which you see in the middle right here, in dark green, the growth of wind power for electricity production, to produce hydrogen for all kinds of applications in fuel cell vehicles. In Aberdeen, they have a city bus system with hydrogen fuel cell buses and also hydrogen powered cars. So next slide, please. So the good news is there is massive solar photovoltaic and wind power development globally, represented in these two plots. Now, these plots are virtually impossible to interpret. They're kind of meaningless, but together they show there's a very, very large amount of renewable energy, and they show a rapid growth rate in the last decade or two. Despite all this development, what we have is the continual equivalent power output from these two renewable technologies of about 350 gigawatts, which is about the output of 350 average nuclear reactors. But these and other industries are growing so fast that in only a few years, the solar and wind electricity generation will exceed all the world's nuclear power plants. Despite that rapid development, we're only adding about 40 gigawatts of continuous equivalent power from these two renewable technologies per year, which is not quite enough to meet the need of 100 gigawatts of displaced coal-fired power in carbon emissions to meet climate targets. So just to translate these kind of meaningless plots into something maybe more visceral, next slide, please. I've got a Google Earth image of Boston in the upper right and Worcester in the middle left. And these four blue squares show the area in square miles covered by newly installed photovoltaics each year of 2016, 2017, 2018, and 2019, with over 200 square miles of photovoltaics in 2019 alone. Next slide, please. So this is just some example of some of those solar power installations. In California, the lower center is 13.5 miles across. It's not completely filled in by any means. We have large made in the pattern of some panda bears. But a lot of these images, most of them are from India. Well, there's been huge amounts of solar energy development. One reason for that is that the power when we lived there and when I was teaching at Pondicherry University was off more than half the time in the rural location in which we lived. And so any power added to the grid was very much in demand and helped, even if it was itself intermittent. Over 40% of the electricity used at the university was used for air conditioning. And so the addition of large amounts of daytime power was a big help indeed. In fact, today, the rural location where we lived has got nearly continuous electric power. But the reason for the construction of all this solar power in India and in other places generally does not have to do with climate. In this case, it has to do mostly with speed. There's also nuclear power development in South India with nuclear reactors at the southern tip that broke ground in 2002 after the planning and design stages. The first reactor came online in 2013, the second in 2016. The full daytime output of one of those reactors was matched by a solar power plant that was constructed in only 9 months. And so this issue of how fast you can develop these things is really important when we consider the deadlines for climate targets. But in this case, these developments were not primarily done for climate reasons, but for the rapidity of development. Next slide, please. I wanted to move now to illustrations of the magnitude of the problem we have to solve and that we have to solve in the next few decades. And I point out to the students that this is during their careers. So to put things in perspective, the world produces about 5 cubic kilometers of oil every year. And on this Google Earth image with Boston in the background right and Worcester in the foreground, the blue boxes there, each one represents about 1 cubic kilometer. We produce globally about 6 cubic kilometers of coal. We produce about 2 cubic kilometers of gas as oil equivalent of volume. And we pour about 6 cubic kilometers of concrete every year using cement that's made by driving CO2 off from a limestone. So all of these are major global industries, and they are major global carbon emissions industries. You may have heard of carbon sequestration, where the idea is that we take CO2 from, say, a power plant and sequester it underground and out of the atmosphere. And as a gas, even a compressed gas or a supercritical fluid, that would take up unrealistic volumes in the subsurface. So to put it in perspective, if you wanted to take all of human carbon emissions and turn it back into limestone, into rock, you'd have to build about 25 cubic kilometers of limestone every year. So multiply these blue boxes over Worcester by 5. That would amount to well over 8 cubic miles of material. We'd have to build Mount Everest from sea level up every year just in limestone to deal with human carbon emissions. Next, please. So another way to put it, some of you may be familiar with the Keeling curve on the left, which is the longest running CO2 record from Mauna Loa, a location chosen to be away from industrial sources of CO2. But there are hundreds of records like this from around the world now. When I was born in 1961, I hate to say it, we were at about 315 parts per million CO2 in the atmosphere. Now, this year, we peaked out at about 415 parts per million CO2. So that 100 parts per million rise in atmospheric CO2 concentrations is near 30% of what existed when I was born. And at 415 parts per million, it's easy to calculate how many watts per meter squared on the planet that produces an extra energy input, or I should say reduced energy output of the planet to warm it up. And that amounts to, over on the right, where it says 415, on that line, it corresponds to over 1,000 terawatts. Now, to put that in perspective, the sun provides us with about 122,000 terawatts. All of human civilization runs on a power of 16 to 17 terawatts. So in the process of doing that, we make cumulative changes to Earth's atmosphere that result in 1,000 or more terawatts of forcing, or essentially retained heat. That's the equivalent to running over 1 million average nuclear reactors. There's less than 500 in operation in the world now. Over 1 million of them to producing electricity, all used exclusively to produce heat. Now, of course, there are mitigating factors such as aerosols and sulfate aerosols that actually reduce solar input. So maybe it's only about 500,000 nuclear reactors worth of electricity producing heat. It's still a staggeringly large amount of energy input to the planet relative to all of human power usage. Next, please. So this is an attempt to simplify and express the problem. Tomasz Stocker published this back in 2013. And if you look at the plot on the right and look at climate target in degrees C and look at the number 2. So we know the Paris Agreement, the goal is to reach 2 degrees C, or limit warming to 2 degrees C. In order to do that, according to Thomas Stalker here, if you follow at the level of 2 over till you hit the 3% line, that means that you have to reduce carbon emissions 3% annually, starting in the year 2020, if you follow that down to the bottom of the plot. And in 2013, that was staggering. 2020 has now arrived. 3% of emissions per year would amount to shutting down 100 gigawatts of coal-fired power plants every year with no carbon emissions replacing them. And that's considerably more than we're displacing with renewable energy now. The problem is there's a deadline. So if you have 2 degrees C, if you follow that over to 5%, you'd have to reduce at 5% per year starting in 2030. And if you follow it all the way over to the hard red line, that's basically when it becomes impossible to grow anything fast enough to meet the deadline. Now, this estimate was made on the basis of some fairly conservative assumptions, and it turns out that it's worse than that. So we've got a very short-term looming deadline in which mitigation becomes essentially impossible. And that means we have to do this using existing technology. We do not have the many decades it took to develop solar photovoltaics from their beginnings in the 1950s to the scale we have today. So that means we have to use technologies that are already at the global scale. That means wind, solar photovoltaics, solar thermal, hydroelectric, and that's usually done by replacing turbines with more efficient within existing dams. To some extent, geothermal and biofuels, if we choose the right one, they're not all a good idea. But we cannot wait to develop new technologies to do this. We can't wait for new technologies to save us, in other words. We have to do this with what we already know. Those new technologies will be really handy in a couple of decades. But right now, we have to operate on the basis of what we already have. That may include carbon sequestration, but right now that industry is small and growing too slowly to make a big impact. Next slide, please. So we've all heard of the massive fires in California and Oregon and Washington going on now, the massive wildfires in Australia in our spring, their fall, earlier in 2020. I want to show you some wildfires in other places less expected. On the left is a view from suburban Glasgow, Scotland. And on the right is on Tasmania, where the Huon and other pines, some of which are, examples of which are more than 2,000 years old, the tree rings show no evidence of fires until now when they're burning. The point being that not only in places where wildfire does occur, just not at this scale, naturally, but in places where it's virtually unknown, wildfires are also taking place. Next, please. There had to be a slide about the current wildfires. On the right is earth.nullschool.net, which I find to be a very handy website, showing PM 2.5 particulates in the western United States from fire smoke. And the direct satellite image on the lower left of fires in Oregon and California, providing a very opaque smoke blanket over the Eastern Pacific. And then my former stomping grounds, this is a view from Fort Collins, Colorado. It looks like it's late sunset or very early morning, but that is noontime under a massive hundreds of square mile smoke cloud with ash falling out of the sky. In the last 10 or 12 years in our time there, or nearby in Laramie, Wyoming, we had an increasing problem with smoke during the summer, either locally or blowing in from the West Coast. But I never saw anything like this. Next, please. Other indicators, there are many others. This is the loss of ice mass from Greenland and Antarctica in gigatons. So 4,800 gigatons of ice from Greenland in the last 18 years, 2,800 or so from Antarctica. Each 1,000 gigatons corresponds to about 2.5 millimeters of sea level rise. And these are not the only sources of water to the oceans. And in fact, a lot of the sea level rise we see is from thermal expansion of seawater. So this translates to more sea level rise than the 2.5 millimeter indicates. So sea level will be rising. Next, please. Another indicator that's not even climate, the red shows the CO2 in the atmosphere concentration rising as we saw before. The green shows the CO2 concentration in near surface seawater. And the blue shows the drop in pH of that ocean water, slight acidification or going in the acidic direction of seawater, which basically makes it much harder for clams and corals and all the organisms that make their shells from calcium carbonate to do so. So this is having a major effect on the ocean ecosystems worldwide. Next, please. So this is a landfill outside Casper, Wyoming. It's in the news recently because replacing old wind turbines. We're getting to the point where early projects with relatively small turbines are being replaced by much larger turbines. And the point here is not just wind turbines, but that renewable energy technologies are not themselves free of consequences. So there's a tendency for people to divide things into black and white and say, you know, fossil fuels bad and dirty and renewable energy green and good. But the fact is all technologies will have environmental impacts of one kind or another. And whether it's mining new kinds of metals and rare earth elements and things for some of those renewable and frankly computer technologies, or lithium for batteries or what have you, everything will have its environmental consequences. So our choice is a difficult one between different kinds of impacts. There's no such thing as something that doesn't have impacts. Next, please. So I want to finish the presentation with this slide, which is very complicated, but it's similar to the one that showed the need for 3% of emissions reductions per year. The conclusion of the paper I took this from is that we need to reduce carbon emissions by about half every decade, which turns out to be considerably faster than 3% per year. This is complicated. It shows emissions, positive emissions to the atmosphere on the left and negative emissions. For example, in blue is CO2 soaked up by the oceans. It turns out that a significant quantity of our carbon emissions dissolve in seawater every year, which leads to that ocean acidification problem. The basic point of this plot, though, is that to meet a 2 degrees C global warming target, we not only have to reduce emissions down to near zero this century, and most of it in the next 30 years, we also must reduce, for example, forest fires and land use change that is burning rainforest and things like that. That's the dark black wedge in the left. And we have to have carbon sinks. We have to have negative emissions. We have to have technologies that can take CO2 out of the atmosphere and sequester it away from the atmosphere in order to meet that target. So the message here is basically we're on a deadline where things have to happen a lot faster than they would have starting several decades ago. We need to use less energy, particularly less direct fossil fuels in transportation, home heating, and things like that. We need to electrify the economy. That leads in general to much more efficient energy usage. We need to try to grow forests and other forms such as soil carbon of stored carbon and grow biomass that lasts and doesn't burn up, we hope, in forest fires. And we need to support innovation, things like thin film photovoltaics, offshore wind power that's a lot more efficient, earth abundant materials. Life on Earth has figured out how to use solar energy to support itself using things like carbon and nitrogen and so forth, and not rare things like tellurium and tantalum. So I think there's something that's cut off here, but so I want to stop talking in formal presentation with this and try to answer some of your questions.
Carrick, thank you very much. I feel like I learned a lot in the last 30 minutes, and I also got really scared. So thank you for that.
Well, one important point is that there is large-scale renewables going on, or renewable development going on, and there's large actions being taken. Really, we just need to speed them up a bit to meet these targets. It is not the case that there's no hope.
That's always a good thing. So let me get to some of the questions, and folks can feel free to log more questions into the Q&A. I think we'll have time to get to quite a few of them this evening. But the first question I have is, should the U.S. enter back into the Paris Agreement?
I think it should. The Paris Agreement is a collection of nations who are making promises about reducing carbon emissions, and some nations do a better job of keeping their promises than others. And so the real key is, are we going to actually keep those promises, and are we actually going to take the actions that we need to take to meet those emissions reductions targets? So I would say, membership in the Paris Climate Accord doesn't guarantee that. We need to actually do things.
So now I've got a couple of questions regarding recycling. It says, what industry is doing the best at recycling? Is it transportation, clothing, technology? Where do we see the most advances?
There is a lot of discussion, as I'm sure you know, of the circular economy and increasing our ability to mine our own civilization for the raw materials for the future. Certainly some countries do better than others. The United States is not particularly good at this. So let's see, for example, household recycling, cans and cardboard and glass and things like that. For example, in Laramie, Wyoming, we were recycling glass for years, but they shut it down because it costs so much to truck the glass down to the Denver area that it was just not cost effective to do that recycling. So the value of recycled products is a problem in the US. In the US, we're really poor at recycling food waste. So when we were living in India, there are now hundreds of thousands of these installations in India, but I can think of a couple of restaurants we visited where the food waste from the restaurant goes into a bioreactor that produces essentially natural gas. And the one restaurant gets 4 hours of its cooking fuel every day from its own food waste. The first time we visited, second time we visited a couple years later, they had 2 of them. And what was amazing to us is that didn't smell bad. It was not a problem. It may come as a surprise, but we spent 6 months in India and never got sick from the food, because things are radically different. Partly that's due to widespread use of UV water treatment. So that all little restaurants, so I could go to these restaurants and have a salad and I didn't get sick from it. But so this development of small scale, business scale, restaurant scale biogas is widespread. And it's a technology that is going the direction of back to places like Europe, because when we were in Munich, Germany, they were building larger plants to use food waste and other bio waste to generate natural gas, essentially. So at that time, this is 2016, there were 12 filling stations for cars providing natural gas for vehicles, and that network is expanding as well. So we produce a lot of food waste in the US, and a lot of it goes into landfills where it turns into methane and gets emitted to the atmosphere, which is a lot worse thing to emit to the atmosphere than CO2 in the first place. So in general, we need to develop recycling, but we have to be careful. I do remember recycling batteries when we were living in Switzerland until some investigative journalists went to follow what happened to the batteries, and they found that they went to a landfill in Eastern Europe somewhere and were never recycled. So, but we've also seen really encouraging things like recycling of copper from wiring in buildings, a lot of recycling, and not just here, but in India and other places as well. And recycling of, those Tetra Paks that are cardboard and plastic that you can buy juices and things in. In a way, they're kind of an environmental insult because you can't easily recycle the cardboard or because of the plastic in them and so forth. But there's a company now that builds corrugated roofing from shredded Tetra Paks, gluing them all together in corrugated roofing panels. So that's the kind of recycling that can really work. In India, we saw a massive plastic recycling system that worked really well. And I have to say, one of the messages here is that places like India have to admit that they're doing a lot better of job of some things than we are. In plastic recycling, there's like a 5 rupee deposit on plastic bottles. And so there is a economy in people gathering together every plastic bottle they can find and bringing them to recycling. And I calculated that if that were a carbon sequestration process, because we also visited dumps in India that tended to be on fire, where the plastic in the dumps was burning, by preventing that from happening, that would have been one of the largest carbon sequestration operations in the world, simply by recycling all that plastic.
So another recycling question, but probably a little bit quicker one, is why can't the turbines be recycled? Why are we putting them in landfills?
Oh, that's a good question. Those fiberglass turbine blades, it's really hard to undo. Or let's put it this way, we have to be very careful about what carbon emissions come from doing these things. It would be unfortunate if we had more carbon emissions from the processes of taking apart, of countering entropy than we get from producing the turbines in the first place. So it just turns out to be neither cost effective nor emissions effective to recycle those blades. That doesn't mean we can't come up with better processes in the future. But for now, the profit margin is minimal on the turbines, and the easiest way to generate more power per dollar invested in the turbine is to make the turbine bigger. And so small blades don't fill that bill.
Thanks, Carrick. This was a different question. This is more about design. And a very WPI question, I might add, how can we best educate mechanical and electrical engineers about sustainable design?
Oh, goodness. That's a really good question. Well, I would say that we can take advantage, and I would say in reality, we already do. A lot of the projects at the Global Project Centers deal with issues that are climate related, but also sustainability related more generally. But there's so many ways that, we need, I would say in a very broad sense, climate is one of the big issue of the 21st century. But climate is often a way of intensifying problems we already have, right? Of food scarcity, of natural disasters, of energy and things. And so we need to apply some of the other inevitabilities of our world, such as the so-called smart world, right? Where we have increasing computing power that can be applied to things that we haven't been able to imagine in the past, such as very sensor-driven large amounts of data processing going in, say, monitoring and reacting to temperature changes to control HVAC in buildings, to control lighting. I'm thinking here of major factory floors or warehouses where keeping the lighting on all the time is a major power draw, but they basically install a system where the lights come on just where the forklift is going, and otherwise they're off, and saving a lot of energy. So there's all kinds of applications in data science and computer science and sensors and infrastructure that we'll need. So another one is autonomous vehicles, right? I think what we're learning is that it takes a lot of computing power to even approach that problem. And it's probably not going to be possible to carry all that computing power on a single vehicle. Especially since, as many of you know, the Moore's law of the rapidity of the increase in computing power is no longer applies because we're hitting the limits of our silicon and photolithographic technologies. And so that means that we're probably going to have a partly infrastructure solution in which there are so-called electronic guide rails and things like that. So we're talking about massive increases in the computing power and the algorithms and the systems engineering that are needed to essentially reduce that energy usage in our infrastructure and buildings and transportation. So I think there's applications for engineers of all kinds in that new world over the next few decades.
Thank you. A couple of questions that are fairly tied, and I'm going to try to weave them together, but we're getting some really good political questions here. And one is, do you think it's possible to reach these carbon targets by purely industrial or technology change, or is government policy intervention going to be required? And I'm going to combine with that since science is under attack, how does the real data make that policy change occur?
Oh, goodness. So my answer to that is probably going to be unsatisfying, but the fact is, the technical problem, the scientific problem of climate change is the easy part. The hard part is actually doing something about it, because that does require us as people, as societies, as governments to make changes in our lives and the policies we run them by. So yes, that is the problem, essentially. You cannot separate climate change from the geopolitical and frankly social justice implications and consequences. So, think about the reactions to a few thousand people, desperately poor people in caravans approaching our southern border, or the migration from Syria and elsewhere toward Europe in the last few years. And then think about sea level rise and the threats to agricultural production in, say, Bangladesh, low-lying, the Mekong Delta, the Nile River Delta, where there's another 50 million people. As sea level rises, as environments like Central America dry out, we're facing the migration of hundreds of millions of people that will make today's situation pale into nothing by comparison. And it will affect us too. Some of you have probably seen, for example, the New York Times article yesterday about migration in the US and the effect of wildfires and flooding, the socialization of insurance, right? For example, Florida, in which after Hurricane Andrew in 1992, insurance companies were pulling out, so that the state created a state-run insurance system that at one point in 2012 had about, what was it, $511 billion of liabilities. California is moving toward that in its reaction to wildfires. So that policy and how we deal with just insurance for houses and where and why we do that, that is really key. The climate impact the poor the worst, and in countries near the equator, take India. My colleague at Pondicherry University, his father is a farmer in the mountains of southwestern India. The impacts, it's not as if it's really warmer there, but it's a very monsoonal environment. And so, for example, he lost all his banana trees because there was a wind event. This is unheard of. When it rained outside in the dry season, when it wasn't supposed to, that can create flooding and big problems. So these are impacting small farmers. It's impacting the Midwestern United States, water availability there, water availability in California. These problems are huge, and they are sometimes a matter of policy. I would also look at the example of electric power policy in South India, where Electricity is provided for free to the poor farmers in the countryside, but the electric power was off. The grid was off more than half the time. So what do the farmers do? They have wells with pumps in them, and they just turn them on. And when the power's on, the pumps run, and they pump fresh water out of the wells. Because you can't predict when the power is going to be on and off. Well, that means that essentially all the wells get overpumped, and there's saltwater incursion along the coasts. So the point is that policy really is central to the whole thing. And I don't have an easy answer for you about how that will work in the United States moving forward. I will say that the rest of the world is, as you've seen in some of these slides, moving on with its solar and wind and renewables development. And people are questioning the value of, say, assets held with oil and gas companies. As many of you may know, there's the private equity investment in the oil and gas operations, such as the fracking and drilling, has produced a lot of oil in the United States, such that we almost climbed back to our peak output from 1970. But that is really expensive oil to produce. And it's not economical on today's prices, which have plummeted down to around the $40 level. So as many of you know, the amount of oil there is not a problem. The amount of oil there is actually tied directly to how much you're willing to pay for it. And if we're only paying $40 a barrel, there isn't that much oil left at that price. So these things are all tied together and play into our policy and economic decisions. And it's hard to get more specific than that with any degree of certainty.
Hey, the questions are coming from WPI alumni. They're going to be tough.
Yeah.
Carrick, you touched on this a little bit in your previous comments, but this question is a little more specific. Where will sea level rise have its most impact, its timing, and what are the geopolitical consequences, which I think you talked a little bit about already?
Yeah, so it's underway. Sea level rise has been evident, frankly, for the last 100 years. It's only resulted in about 10 inches of total sea level rise on average around the planet. It's not the same everywhere because while we like to think of the land we stand on as fixed, it isn't. In places like the Gulf Coast, where sediments naturally are supposed to accumulate, the land sinks. And so if you stop the sediment accumulating, the land keeps sinking from the millions of years of sediments that were deposited there before. And so sea level seems to be rising even if it isn't. Whereas places, say in Alaska or Norway, that were under miles of ice not that long ago during an ice age, are rising because of all that weight's been removed only 10,000 years ago. So that looks like sea level's falling. But on average, sea level's risen 10 inches in the last century. And that rise is going to continue. At the rate we're losing ice mass from Greenland and Antarctica, we're looking at a meter of sea level rise by the end of the century and probably much earlier, because these things are happening faster than they were predicted in some of the models. So that's going to obviously impact the low-lying areas, and that tends to be where poor people live. And it's also, so many of us live near the coasts. And maybe New York City will be able to build seawalls and keep it at bay for quite a while. But other places will not be able to do that. Barrier islands along the Gulf Coast, North Carolina and the Southeast. Poorer communities will probably have to be abandoned, and that's going to happen this century. And it's starting to have an impact on whether you can get insurance, on whether on housing prices and things like that. And if that takes hold, right, we're looking at some pretty big and drastic changes.
That's sobering, thank you. Next question is, with the world population continuing to increase and our resources finite, can we practically control carbon emissions without population control?
I think we can. The population growth rate was at its highest during what we call the Great Acceleration. And it's slowing down now. It was slower in our past. So the great acceleration was the post-World War II, 1950s and 60s. And I've tried to show that the good news is that renewable energies have reached the global scale and are being installed worldwide at an amazing scale. And if we can up that rate just a bit, we can multiply it by a factor of 2 or 2.5. We can meet that challenge despite growing population. For example, the United States population has continued to grow, but its electric power usage has not. We actually, in Wyoming, since I came from there, and it's pretty much a fossil fuel state, right? It produced 462 million tons of coal in 2008 at its peak. This year, that's probably going to be down well under 200 because people don't want to generate electricity with coal anymore, on top of which the electric power market in the US is not growing despite increasing population, despite an expanding economy. And mostly that's because of natural gas instead. But renewables, since they're growing so quickly, will start to pick up. So I believe one thing, that population growth rates will not be as high as they have been in the last 50 years. Partly that's because it's becoming very, very difficult to live in some places. Let's face it, there's a lot of human misery in that equation. But I think also that we have the ability, and we've proven it in global scale technologies now, to displace carbon emissions faster than population's growing.
Thank you. So now a different question. How do you see oil companies changing to meet lower carbon goals?
Well, first of all, I'm going to back up and say the first thing we have to deal with is coal and coal companies. And pretty much that's already underway. All those coal companies in Wyoming have undergone bankruptcy, came out of it, maybe going back into it. And we had a PG&E, not PG&E, that's just one of the companies in the Berkshire Hathaway group that has power companies across the Western US. He came into Wyoming, a coal state, several years ago and said, coal's dead, sorry, but that's the way it is. So then oil companies. Sarah and I spent a lot of time in Switzerland. I was a postdoc there for some time, and we were also at the Rachel Carson Center for Environment and Society in Munich, from which we visited an industry forum at ETH Zurich, where gathering together large companies and their climate-related plans. Shell Oil was there with the VP, General Electric, a bunch of other companies of that scale. And Shell Oil said basically, yes, we see the writing on the wall, and we are looking at becoming primarily a gas company more than an oil company in the near future, and then transitioning from there possibly into hydrogen. But I think many of those companies are seeing, especially now with the pandemic and the consequences of the pandemic, and I think at one point ExxonMobil stock price had dropped by a factor of 3 over the summer. So they're not looking like as good investments as they may have looked in the past. And they are, many of them, you may realize, for example, that BP quite a while ago had a solar energy arm. In fact, I bought a number of BP solar panels at one point. So now they sold that, but I think oil and gas companies see that they're going to have to change their business model. And moving from oil to gas is one way to do that, because gas emissions per unit of energy produced are lower than oil. It's clear that with the rapid growth of electric vehicles, for example, American demand for gasoline is actually not rising and maybe dropping. So these changes are underway, and it's not clear that post-pandemic, we're going to be going back to the levels we were pre-pandemic.
Thank you. This question's a little more detailed. How about material science? The lack of recyclability of wind turbine blades is a function of the material it's designed from. We have to teach engineers, students and practitioners to consider recyclable and reuse of materials, including separation of disparate materials from each other during the selection and design processes in order to reduce and eliminate problems like this. This is more of a statement than a question, I think. Problem is that we often don't have the data to do that. Are there opportunities for IQPs and MQPs here?
Oh, goodness. Well, I think so. I think you're absolutely right. The processes, the materials that we design, if we can come up with a process, say carbon fiber blades that could be made cheaply enough to be practical, are they burnable, for example? Can we use the turbines at least, for example, living outside Zurich, they don't have in Switzerland a lot of space for landfills and things. They take most of the refuse and they take it to a cogeneration plant and burn it. That'd be everything. They burn everything at super high temperature. So then it becomes a matter of breaking up the turbine blades and making them out of a material that can be used in that way. So I think with wind turbines, one of the biggest issues is actually the towers themselves when they cease to be useful, made of steel. That's probably more recyclable than the blades. But the big thing to me is these really big, 9, 10 megawatt turbines are going from windings to direct drive, meaning they're using super massive magnets made with what? Rare earth elements. That stuff has got to be recycled. There's no way we can use those on those scale without recycling those materials. But in general, the circular economy is a challenging issue, right? Because we kind of, in a way, have to overcome entropy and exert and expend energy to recover those materials we used in making things. We have to mine our own built environment. We have to mine materials from the IT and computational circuits of the past. And there is a heck of a lot of engineering and design that needs to go into that and needs to happen soon. And so I'd say there's a lot of scope for IQPs and NQPs in that area, because there's a lot that we need to learn to do that efficiently.
Carrick, I've got 2 more questions if you have the time. We're at 7:30, so we'll try to wrap this up in a couple. The first one is, what is the most efficient way to bring large-scale green energy projects to smaller third world countries?
Oh, goodness. The amazing thing to me is that it's already happening to an extent that may be surprising. And it's part of geopolitics. So we out in rural India, to that example, but also examples in Africa, lots of small villages, only, 40% of the population of India, which is like 400 million people, more than the population of the United States, aren't on the electrical grid at all. They're not formal users of grid power. They don't pay a power bill. And that doesn't mean they haven't surreptitiously tapped into somebody else's power. But there are a lot of isolated small villages, and out in them, what I see is a lot of small scale solar. I mean, a panel that's, this big, that runs a small battery that is a light or two inside at night. And it's hard for us to imagine how revolutionizing that is. I've seen, in India, you might stereotypically see an ox cart, being pulled forward slowly by an ox with a bunch of hay or something in the back. And yet the person on that cart has got a cell phone and has a light at night because he's attached to a car alternator. And this is the engineering work of people in institutions and engineers that find a way to use, say, old car alternators to provide power with a little battery and a car alternator on an ox cart. The ability to have a light in the evening is revolutionary to whether you can work on something, whether kids can do schoolwork after it gets dark, something that we take for granted that so many hundreds of millions of people in India and elsewhere are solving with really small scale solar. And it has another advantage that we don't think of as well, which is autonomy. In other words, they may not trust the power companies. They may live in an environment where there's a certain amount of corruption, and they're not really keen to be tied to a power company. But if they can produce their own power on their own direct expense and stay autonomous, that has a lot of value to some. So I've got, whole presentations full of slides of little solar panels on huts and things in India, but also take Zimbabwe. There's a major hydroelectric project on the border, I've forgotten now, with Zimbabwe and Zambia. That's a 650 megawatt hydroelectric dam, but it's only producing 200 megawatts or less because of drought, an example of climate imposed limitations on power production. Despite not being exactly a rich country, Zimbabwe is also having large-scale solar development. Let's face it, funded in part by Germans and funded in part by China. So that's how it's actually happening. Not that it's the same kind of country, but Chile is also having massive solar power development. And that's a tremendous place because it turns out not a lot of people realize that solar photovoltaics are much more efficient when they're cold than when they're hot. So if you put a bunch of solar panels in the Atacama Desert where it never rains, where it's never cloudy, and where it's cold because it's up at high altitude in the Andes, it has some of the highest capacity factors in the world. So that's a tremendous power source in a place like Chile. The disadvantage in Chile is that it's a very long, thin country with a lot of power transmission needs that go with localized power generation. But I hope that answers some of the question about
Thanks, Carrick.
developing
I'll
countries.
end with this one, which I chuckled when I read it. Knowing what you know about climate change, where is the safest place for me to live in the United States, i.e. will not flood, burn, get too hot, or too cold to be comfortable?
Well, that's a good question. If you figure it out, let me know. So if we look at the recent New York Times article, look what's going on in the US, people have moved toward the danger zones in ways that they haven't in other countries. So what was it? A 5 million person increase in coastal Florida, despite the flooding that will be inevitable in the coming decades. So many people moving to California and the Pacific Northwest and the Mountain West, where all the fires are happening. The threat, if you really think about it, the fact is, if you drive out to the Midwest, Nebraska, there's a lot of corn. And in a lot of places, that's not grown by natural rainfall. It's grown by tapping aquifers all through the Midwest. And they will not last forever. They're already being hitting limits, which means that the water you pump out of deeper and deeper gets more and more saline. So there's the threat of a repeat Dust Bowl if we're not careful. So aquifer recharge is a really important issue, and it's going to be difficult when we've got limited water resources. So where to live? A lot of people will need to move north. They're talking about the resurgence of places like Ohio with extra capacity in the north along the Great Lakes and things like that. Because we're talking really, if you go back to that New York Times article, it's talking about the climate at Buffalo becoming more like the climate in Tempe, Arizona. But think about this too. Take New England. It has not entered our darkest dreams yet that we would have massive wildfires like in California and Australia. But we live in a highly wooded environment. In fact, back in the early 80s, we used to talk about the missing carbon sink because a lot of the emissions that we knew were going into the atmosphere weren't showing up in the atmosphere. And part of that was because of the regrowth of forest in New England. If you look at pictures of New England, New Hampshire from 1940, what you see is a lot more open land than you see today. And that was soaking up a lot of carbon. In fact, I think I mentioned this, if you took the area of New Hampshire, Vermont, and Massachusetts and started a new forest that size, that would soak up that 3% of carbon emissions. But on the other hand, look at this summer. It's been very dry. There were actually fires in the 40s in Maine. We've been good at fire suppression here as well, but, don't get too complacent. New England, if you had, and you could, have a massive wildfire, think about how many of us live strung out along 2-lane roads through the woods, where evacuation will be difficult and confusing, and which way to go as the flames move quickly. So I think one thing is we have to realize that things we think of as impossible, take the case of Scotland, may actually become possible. We went to Scotland to prep this course for students, and it was raining and it was muddy where we hiked and things like that. We thought we have to warn the students that it's going to be muddy and wet and cold, even though it's June. But the next year, when we took the students there for over 3 weeks, there was virtually no rain. It was hot and sunny the whole time. And the students were complaining that they had jackets, but not enough shorts and t-shirts. The one day it was cloudy was the day we were taking what we jokingly call the Hogwarts Express. It's the steam train that you see in the Harry Potter movies. But the days before and after that, they wouldn't run it because of the danger of fires being sparked by the ashes coming out of the steam train. So you wouldn't think of this in a place like Scotland that's known for being wet and cold, but things are changing. It's not like that. And it has a direct impact on tourism in this case. So again, I think it's realizing that what was true in the past may no longer be true in the future. And the seeming, million-acre wildfire seasons in California, how long will it be before they take place in New England?
Well, Carrick, I want to thank you so much for your preparation tonight. We really enjoyed hearing this. It was sobering indeed, but thank you for enlightening us on this subject on Zero Carbon Day. Really appreciate it.
Well, thank you very much. And I'm sorry about the doom and gloom. We did end up doing a lot of that. But I want to go back to the message that there are things we can and are doing that we just have to ramp up a bit, and that there is still a way to deal with these problems.
Thank you. I also want to thank our audience for some excellent questions. This is one in the series. We did one on 5G about a month ago, and we will have some others coming up in the future. Hope you can join us for them. In the meantime, I encourage you to sign up for Tech Connect. I think Jen's going to pop that into the chat so that you can see the link there. It's a great way of keeping in touch with alumni, but it also has a job-seeking function, a mentoring function, and a lot of other opportunities to work with other alumni. And I think that brings us to a close. So I'd like to thank everyone. I want to call attention to Jen and Aubrey, who helped put this together. And I know they're invisible to everyone, but we really appreciate your support. Thank you, folks, and have a great night.
Thank you very much. Thanks to all of you.